I'm not just talking about some big computer model sitting on a server somewhere. We're talking about a global, planet-scale operation with traffic managers, massive clusters of GPUs, and this constant, delicate dance between speed and cost.
You see, the entire system is built around one fundamental conflict. On one side, you've got low latency. That's making the experience feel instant for you. But on the other side, you have high throughput, which is about efficiently managing the astronomical cost of doing this for hundreds of millions of people at once. Literally everything we're about to talk about is a clever solution to this big balancing act.
Okay, so let's dive into the first huge problem. These big language models, they don't actually understand words like you and I do. They're math machines. So the very first question they had to solve was, how on earth do you translate the beautiful, messy, complex thing that is human language into cold, hard numbers?
The answer is a process called tokenization. Now think of it like this. The model has its own special vocabulary. But instead of just letters, its vocabulary is made up of the most common chunks of text it's ever seen. So it breaks your sentence down into these chunks, or tokens, turning it into a sequence of numbers it can actually work with.
So how does it build this special vocabulary? Well, most modern models use something called byte-pair encoding. It's pretty clever, actually. It just scours a massive amount of text, finds the most common pair of letters, like T and H, and merges them into one new token, th. Then it does it again and again and again, thousands of times, building up a super efficient library of text chunks. But here's the catch. This whole process, as necessary as it is, it's also the source of so many of the weird, quirky, and downright frustrating things that these models do. The famous AI researcher Andrej Karpathy once joked that tokenization is the root of all suffering in LLMs. And you can see exactly why right here. Because the model thinks in these chunks instead of individual letters, it can get really tripped up on simple things. Ask it to spell a long, weird word, and it might fail. Ask it to reverse a word, surprisingly hard for it. This is also why it's often terrible at simple math that involves characters. And it's a huge reason why these models can struggle with languages that get broken up into way more tokens than English does. Okay, so our text is now a string of numbers. Got it. But that leads to the next big question. How does the model generate a response so quickly? How does it avoid having to recalculate everything from scratch for every single new word? Seriously, think about that for a second. If the model is generating the sentence, "Time flies fast," after it's generated, "Time flies," does it have to go all the way back to the beginning and reprocess "time flaws" just to figure out that the next word is fast? The crazy answer is that without a very clever trick, yeah, it absolutely would.
And the solution to that huge inefficiency is something called the KV cache. Honestly, the easiest way to think about it is as the model's short-term memory. Instead of re-rating the entire conversation every single time it generates a new word, it stores the key calculations for all the previous tokens. That way, it only has to do the math for the newest token, which makes the whole process dramatically faster.
So, we know how it generates tokens fast. But how do those tokens get from a server in some data center all the way to your screen to create that slick, real-time typing effect? Well, the answer is kind of surprising. They use a technology that's been around for ages called server-sent events, or SSE.
And SSE is absolutely perfect here. Think about it. Generating a response is a one-way street. The server just needs to push words to you. That's exactly what SSE was designed for. It's way simpler than other options like WebSockets, it works over normal HTTP, and it even reconnects automatically if the connection drops. It's just the perfect, elegant tool for the job.
Okay, so let's zoom out now from the low-level stuff and look at the big picture. How does all of this come together into an architecture that can serve hundreds of millions of people all around the globe, all at the same time? So the moment you hit enter, your prompt goes on this incredible journey. First, it hits a global traffic manager that sends you to the closest, fastest data center. From there, it goes to a layer of request handlers. And then finally, it gets routed to one of the massive clusters of GPUs that does the actual thinking.
And let me tell you, the challenges at this scale are just mind-boggling. You're not just managing thousands of GPUs, the system has to remember the context of your specific conversation, run safety checks on both what you type and what the model says back, and handle huge, unpredictable spikes in traffic, all without you even noticing. It's a massive undertaking.
And just to give you a taste of this scale, let's look at just one piece, the database for user chats.
OpenAI managed to scale a single main Postgres database to handle millions of queries every second. They did it through insane optimization and really clever engineering. That's just one piece of the puzzle.
Now, what's really fascinating is how all of this is causing a giant shift in the world of AI compute. The needs of the entire industry are changing, and they're changing fast. You see, there's a huge difference between training a model and running inference. Training is like building the engine. It's this massive one-time job that takes weeks on a supercomputer where you just want to cram as much data through as possible. But inference, that's answering your prompts. That's like driving the car every single day for millions of people. It's continuous and has to be incredibly fast and responsive. And because of that difference, the whole game is changing. Training a model is wildly expensive, no doubt. But the total amount of computer power needed to answer billions of questions from users every single day, that's inference, is set to become 5 to 10 times bigger than all the training compute combined. Answering questions is becoming a much bigger deal than teaching the model in the first place.
So after peeling back all of these layers of code, hardware, and engineering, what's the big takeaway? What is the real product that we're all using?
Here's what it boils down to. The real product isn't just the AI model itself. It's the entire, globally scaled, obsessively tuned system that gets that intelligence to you, instantly and reliably, no matter where you are in the world. The magic, it turns out, is just as much in the pipes as it is in the AI.
And that leaves us with one final really big thought to chew on. All of this incredible engineering, all of it, is driving the cost of getting an intelligent answer down, closer and closer to zero. So what happens then, when an AI-generated answer becomes virtually free? What new ideas, what new companies, what new possibilities will that unlock for all of us?